All right, chemistry and honors chemistry. This is the answers video to day 48. It's been out there a while, partly because I didn't get this video up for you. So now here it is. Finish this up and get it turned in. I want to get it back to you because you have a test on Friday, which will be April the 22nd. So get it in, get it back, and I'll get it back to you, and you'll have to study for the test. So let's go ahead and read some brief notes here. So gases have no fixed shape or volume. They can be thought of as atoms or molecules that have enough energy to break away from other atoms or molecules, and often they float in the atmosphere. Generally, but not always, gases are suspended and float in the atmosphere. So you can have a bottle of perfume with a lot of perfume molecules, whatever those are, and you open the bottle and 15 minutes later they fill the entire room. You can smell them throughout the room. They take up the shape of the room. So that's what a gas does. So we will deal with gas laws in the coming weeks. Well, actually we have done that, but for now all you need to know is the following important relationship: that at 0 centigrade, that's the freezing point of water, and 1 atmosphere, that's the air pressure where you live in San Diego, 1 mole of any gas occupies a volume of 22.4 liters at standard temperature pressure. That's called standard temperature pressure. So think of a 2-liter soda bottle. Now think of 11 of those. That's 22 liters. And that's, if you open those up and just let air go into those, then those would, that would be 1 mole of air. All right, so 1 mole any gas equals 22.4 liters. And that's at standard temperature pressure. All right, so let's go ahead and do some of our stoichiometry problems here. All right, and a few corrections that I made in class. Well, first of all, let's look at this. So we have down here our chemical world, and this is the world of moles. The chemical equation speaks in terms of moles. I'm going to put a 1 there. It's 1 mole and of C3H6O, 4 moles of O2, 3 moles of CO2, 3 moles of H2O. Remember, a mole is just a number of particles, a number of molecules, a number of atoms, whatever, a number of whatever you're talking about. All right, and so that's the only relationships chemical equations understand, is these numbers. If you want to think in terms of molecules, you need 4 oxygen molecules for every one of these acetone molecules. If you put in 4 molecules and react it with 1 acetone, you're going to get 3 molecules of carbon dioxide and 3 molecules of water. Or if you multiply all those numbers by 6.022 times 10 to the 23rd, then you talk about a mole, a big basket of molecules. But it's a number. It's a number of atoms or molecules. Down here we have grams. Now I didn't fill out the molar mass here. We did that in class, so I'm going to go ahead and do that right now. And we have 1 mole of C3H6O is 58.09 grams. 1 mole of O2 equals 32 grams. Now again, remember, molar masses are always 1 mole, 1 mole, 1 mole. Don't get confused by the moles that are in the equation. That's just for this specific problem, this specific chemical equation. But 1 mole of O2 gas is always 32 grams, no matter what the problem is. So don't get confused with that mole right there. That doesn't have to do with molar mass. Okay, moles of CO2, so 1 mole. And H2O, 1 mole. And there you have your molar masses. Now, based on the STP rule that we have up here, 1 mole of any gas equals 22.4 liters. Unfortunately, I left these as H2s. It doesn't matter what the gas is, but let's just go ahead. It's really referring to this. Not H2, any gas. In this case, it's referring to O2. 1 mole of O2 equals 22.4 liters. So I'm just going to X out the H2s. They refer to whatever we're dealing with down here. And these are all gases, as you can see. So what you can see from this that differs from what we've done before is you can enter from grams into the chemical equation, or come out from the chemical equation to grams, just like we did before on previous lesson. That would be day 35, 36, 37. Now we can actually enter another way. We can come in from gases from liters. So liters to moles is 22.4 liters to 1 mole for any of these here. Okay, so it's actually not a real complicated addition to these problems. All right, so let's get going. So how many grams of C3H6O are required to create 6.4 liters of CO2? And I hope you're getting quick at these now. So we need grams of, and that's acetone. So, well, let's just go ahead and call it. I was going to give it an abbreviation, but let's not be too clever here. 6.4 liters of CO2. You start that way over on the right. Okay, so let's put our question mark. It's grams of C3H6O, so here it is right here. And it starts with liters of CO2, so it's up here, 6.4. It's in the liters row, and it's above CO2. So our path has got to be to come down, go across inside the chemical equation, and come down here. So our first conversion or equivalency is going to be that one. Our second is going to be the moles to moles between CO2 and C3H6O. And then our third is going to be the molar mass of C3H6O to come out. Okay? So I'm going to go ahead and just write that out silently, and then we'll fill in our conversions. Okay, so we need liters of CO2 to cancel with liters of CO2, which we did. We now have moles of CO2. That means we're sitting right here in the moles box for CO2. Now we need to come across, and again, it's simply 1 mole of C3H6O equals 3 moles of CO2. Okay, moles of CO2 cancel. All right, and now we are sitting in this box of moles of C3H6O. That's what this says right here. And now we need to come out using the molar mass to get us to grams. Okay, moles cancels with moles. Last man standing is grams of this. So we have it set up right. So now we go ahead and do the math. And we get 5.53 grams. Depending on how many digits you want to go, I don't really care. And that's the final answer. Okay, B, how many liters of O2 at STP are required to produce 17.84 liters of H2O? So you're going liters to liters this time. So we're going to come back here. And it's O2, it's liters, that's what we're looking for. And it's 17.84 liters of H2O. Here's H2O. There's liters. Okay, so again, we don't have a direct relationship liters to liters. So we have to come liters to moles to moles, and then moles back out to liters. So it's another 3-step problem. So let's go ahead and set it up. Again, boxes are optional for you at this point. Okay, just write equivalencies. So our first one is coming from here down to here. It's just 1 mole. 22.4 liters. This one goes on the bottom. It's on the top here. It's on the bottom, so it's this one. Okay, cancel and cancel. You're in moles of H2O. Sitting right here in the moles row of H2O. Now we need to get across there. 4 moles of O2 equals 3 moles of H2O. Okay, now we're in the moles of O2, sitting right here in moles of O2. Now we need to come out to our final answer, and there's the usual conversion for liters. Okay, our last man standing is liters of O2, which is what we want. So now we can start multiplying. There's a simple additional cancellation you can do here. You have 22.4 on the top there, and on the bottom, you just go ahead and get rid of it. So it's 17.84 times 4 divided by 3 is all you need to do. And we get 23.8. Okay, how many liters of H2O? So we're just going to right away come over here. Can be produced by 2.25 grams of O2. So liters of H2O is what we're looking for. Grams of O2 is 2.25. That's down here. So path is through the molar mass to moles, moles to moles, and moles through liters, or through the conversion to the liters of H2O. Okay, now we move to the moles to moles. So it's moles of O2, moles of H2O. 4 moles of O2 equals 3 moles of H2O. Okay. So now we're here and we just have the standard 1 mole equals 22.4 liters for H2O. Last man standing's right there. So 2.25 times 1 times 3 times 22.4 divided by 2.25 divided by 4 divided by 1. Sorry, I've been off screen there a little bit. Okay. Okay, and we get 16.8 liters. And I just see I wrote it all in the wrong place. Sometimes I don't notice that. Okay, so this one goes up here. And this one, I'm going to put here. Okay, you got that? My mistake, but it's okay. We got space. Let me create a little more here by doing that. Okay, so this is this. So now we're going to take this and put it right here. Okay, so let's go ahead and do that. You probably saw that the whole time, and I didn't. That's what happens when you get involved in doing a problem. Okay, so here we go. So this is the one. That was the 2.25. That should have been a decimal point, by the way, not a comma. Okay, all right, so here we go. So how many grams of O2 are needed to completely react with 8.92 grams of C3H6O? So that's one of the old problems. It's grams to grams, old type problems, okay? So here we go. Grams of O2 and 8.29 is here. 8.92. 8.92. 8.92 is here. So we're going to go up molar mass to get to here, moles to moles to get to here, and molar mass to get back out to here. Okay, so let's go ahead and set that up. So again, we're doing this problem down here. Grams of O2. And 8.92 grams of this. Okay, first conversion is the molar mass of the acetone. I start those way over here, especially with acetone. It's a long chemical name. Okay, so we're sitting in the moles box here. Moles to moles is 1 to 4. 1 mole C3H6O to 4 moles of O2. Okay, and finally molar mass out for O2. 1 mole is 32 grams. Okay, so let's go ahead and compute that. 8.92 times 1 times 4 times 32 divided by 58.09 divided by 1 divided by 1. All right, and you get 19.7 for that. 19.7 grams of oxygen. Okay. Okay, how many grams of C3H6O? So let's put that right away over here. Are required to create 6.4 liters of H2O. That goes over here. That's what we're starting with. Okay, so we come here. Liters of H2O is 6.4. How many grams of this is what we're looking for? So we're going to come down through the liters, moles to moles across, and molar mass down to get us to C3H6O. Let's go ahead and do that. Okay, so we're sitting here right now. We need to come across to here. 1 mole C3H6O equals 3 moles of H2O. Okay. So now we're sitting moles here. We need to use a molar mass here to get out to our final answer. Okay, so it's going to be 6.4 times 1 times 1 times 58.09 divided by 22.4 divided by 3. Right, and that gives us 5.53. Okay, we'll move on to the next problem now. Okay, here we go to the next problem. This is the lithium hydroxide neutralizing carbon dioxide. That was the spaceship issue that we talked about, where the way they get carbon dioxide out of the space capsule is to mix it, run it through filters with lithium hydroxide, and it just turns into these substances that they can eject out in space. So that's how they clean the atmosphere there. Okay, so we have our same 1 mole, 22.4 liters. Scratch out the H2s there. And down here we do have our molar masses for everything down here at the bottom. Okay, so let's go ahead. So how many liters of H2 gas can be formed from 4.29 grams? So here we go. H2O. Okay, so we'll go up here. We're going liters of H2 is what we're looking for. It's up here. And it's grams of lithium hydroxide, which is 4.29 down here. So you go up through molar mass, moles to moles, and through liters to get to your final answer. All right, so molar mass first. Okay, now we're going to go moles to moles. There's a 1 there. I'll go ahead and write it in there, and there, and there. 1 mole, just to be sure you're clear. There's a 2-to-1 relationship. Now we're here. We just use the standard liters to moles conversion. Okay, now we multiply 4.29 times 1 times 1 times 22.4 and divide by 23.95 divided by 2. Okay, and that's going to give us 2.0. Close enough. We'll call it that. Okay. All right. Okay, how many liters of CO2? So right away we'll come over here. Are required to completely react with 12.87 grams of LiOH. Okay, so we'll come up here, start with grams of LiOH. And it is 12.87. And we're trying to get to liters of CO2. That's up here. So we're going to come up through molar mass, moles to moles, and then liters, moles to liters to get out. Okay. And all right, and molar mass is right there for LiOH. Okay, right there. In there. Okay, and that takes care of that. We're now in moles of LiOH right there. We need to get the moles of CO2. It's 2 moles of LiOH for every 1 mole of CO2. Okay, and now we're sitting in moles of CO2. We need to get out using this to get to liters of CO2. Okay, so we've got 12.87 times 1 times 1 times 22.4 divided by 23.95 divided by 2. Okay, and that gives us 6.0 for our answer. Okay, here we go. So see, how many liters of H2O? So right away, how many liters of H2O are formed if 89.71 liters of CO2 is completely reacted? Okay, so we come up here. How many liters of H2O? Here's H2O, there's question mark. And 89.71 liters of CO2, there's liters of CO2. So So we're going to come down through liter to mole conversion to get moles, moles to moles, and then moles back out to liters to moles to get to the liters. Now we go liters to liters, and that's 1 to 1. Or moles to moles, I should say. Let me do that again. Moles to moles. Okay. So that puts us right here, and now we just do the moles to liters to get out for water. Okay, so we're going to multiply 89.71 times 1 times 1 times 22.4 divided by 22.4 times 1 times 1. Alright, so you can see we could cancel the 22.4s right there. So it looks like all we have is 89.71 liters. Don't even need your calculator for that one. Again, 89.71 times 1 times 1. We canceled that to make it a 1. We canceled that to make it a 1 times 1 times 1. So you just have 89.71 for your final answer. All right. Okay, how many grams of L2CO3? So Li2CO3, CO3, Li2CO3, okay, are formed if 52.6 liters of CO2 are completely reacted with LiOH. Some students were confused by that. It's just, this is superfluous information. I could have just stopped with completely reacted. I just added, but they are, if you look at the equation, they're reacting with LiOH, so I threw that in there. Okay, they can do that, so you have to kind of be aware of that kind of wording. But the LiOH has nothing to do with the problem. So we're going to come over here. Okay, we're going grams, trying to find grams of Li2CO3. So let's erase this. There's Li2CO3, there's grams, we're trying to find that. And we're starting with 52.6 liters of CO2 right here. So we need to go down through moles to liters to get to moles. Moles, oops, I put this in the wrong place. Let me try that again. It's grams of Li2CO3. So down here, moles to liters to get to moles. Moles to moles, it's another 1 to 1. That makes it easy. And then moles of Li2CO3 out to grams of Li2CO3 down there. Okay. Go ahead and draw my boxes first. Okay, and again, we said it's, so let's go ahead and do this first. So liters of CO2 is going to go on the bottom. Okay, so now we're sitting in the moles of CO2 box right here. We need to get to moles of Li2CO3. It's a 1 to 1. Okay, so now we're sitting in moles of Li2CO3 right here. We need the molar mass to get us out to grams. Okay, grams of Li2CO3 is the last man standing. So I'm off the screen. Let's get on the screen. Okay, see what I did. Okay, moles of CO2. So moles of CO2 here had to go on the bottom. Then we come over here and we have moles of Li2CO3. So with this conversion, moles of Li2CO3 goes on the bottom. This goes on the top. Okay, there you go. All right, so we're going to multiply 52.6 times 1 times 1 times 73.89 divided by 22.4. And that gives us 173.5. And that's our answer for that. Okay. All right, let's keep moving. Okay, so all throughout this lesson, we've been saying that 1 mole of any gas equals 22.4 liters at STP. So let's prove it. So STP means 0 degrees centigrade and 1 atmosphere normal room pressure of pressure, okay? We need to convert that. So to go from centigrade to Kelvin, it's 0 plus 273 equals 273 Kelvin. Okay. Now, why do we need to do that? Because we're going to use this formula, and we have a gas constant called R. So let's define that. It's 0.0821 liter atmospheres over moles Kelvin. We've said what that is. It's a whole bunch of conversion factors rolled together, so that whichever one of these variables, P, V, N, or T, you're solving for, you'll end up with that unit of measure at the end of the problem. So if you're solving for T, you're going to end up in Kelvin. If you're solving for P, you're going to end up with pressure. This thing will make all the other units cancel out. So what it's telling us is that the temperature units we have to use is Kelvin, not centigrade. You can't put centigrade into this equation because it's looking for Kelvin. All right, it is looking for atmosphere, and that's what we have here, so that's good. All right, so what we're going to do is we're trying to show that 1 mole produces 22.4 liters. So we're going to start with 1 mole, a pressure, I should put N equals 1 mole. The pressure equals 1 atmosphere. The temperature is 273 Kelvin. We have R over there. And the volume is what we're looking for. We're going to look for what that volume is, but we're expecting it to come out to be 22.4. That's what we're going to see if that's true or not. So let's see if that's true. So here's the formula. So now we're going to solve for volume. So we do that by dividing by P. Oops, I shouldn't have put that all the way across like that. Tell students not to do that. PV over P and this side over P. These cancel, and you have volume equals nRT over P. Now we're going to plug in the numbers. N is 1 mole. R, temperature is 273 Kelvin. And the pressure on the bottom is 1 atmosphere. So here we get to practice our unit cancellation. So you have mole in the numerator top. If it's only on one level like this and this, it's on the top. So numerator top and numerator bottom. You see it's on the bottom of this ratio here. So moles is going to cancel with moles. Kelvin is also numerator top. This Kelvin is numerator bottom. They have both have the word numerator in common, so that cancels with that. This is numerator top, and again, only one level in the denominator, so that's denominator top. So numerator top, denominator top cancels. The only unit left is liters, and that's what you want for volume. So now we're going to run the numbers. 1 times 0.0821 times 273 over 1. And when we do that, we get 22.4 liters. So at standard temperature pressure, 1 mole will equal 22.4 liters of any gas. It doesn't matter what the gas is. Okay, actually this is where we practice that. I think we did this in class before we did this problem up here. Let's go ahead and knock these down. So numerator top, you just go ahead and label them the first time you do this. This is just meant to be a fun problem. You'll never see units like that. Numerator bottom. So if they have a word in common like numerator and numerator, they can cancel. If they have a word in common like top and top, they can cancel. Denominator, denominator, they can cancel. Bottom, bottom, they could cancel. Okay, so let's look at these two Ks. Numerator top, numerator bottom, they both have the word numerator. Let me go ahead and draw some lines here. They both have the word numerator in common, so they cancel. Atmosphere and atmosphere here. They have numerator top, denominator top. They both have the word top in common, so they cancel. Okay, how about this liter? Liter is numerator top, and this one down here is denominator bottom. They don't have any word in common. Numerator top, denominator bottom, no word in common. They can't cancel. Down here, mole is numerator bottom. This mole is denominator bottom. They both have the word bottom in common. They can cancel. This gram is denominator top, denominator bottom there. So they both have the word denominator. They can cancel. Okay, now this liter, numerator top, and this one is denominator top. They both have the word top in common. They can cancel. Okay, and let's see. Everything has canceled except the gram and the liter. Now, if you've canceled everything on a level, it becomes a 1. So we come down here, it's 1 over this G right here. I'm going to put this in parentheses. All over, and again, these have all canceled on the denominator top. So that's 1 over, and that liter on the denominator bottom. Okay? So now you just have to remember your fraction division rules. The top, you stay the same. The bottom, you flip and multiply. So I'm going to take this and flip it over and put the liter up on the top and the 1 on the bottom. And you multiply those two and you get liter over gram. And that would be the units of measure for that. Okay? All right, let's do this one. I'm going to do this one silently. You try to do it first. Now, here's a little trick. I'm going to just do this the way that I think will make it easier. Anytime I see a square, mole squared, I'm going to write moles times moles. Anytime I see atmospheres to the third, I'm going to write atmospheres times atmospheres times atmospheres. That'll make it easier to do the cancellations, okay? So here we go. I am omitting the little dots for time signs, so any space between it is simply a multiplication. Okay, so I've broken everything out like that. Now you can start canceling. Okay, so we have mole here in numerator top and in numerator bottom. We have Kelvin in numerator top and Kelvin in numerator bottom. We have atmosphere, numerator top, numerator bottom. Okay, so let's look for grams. Grams is down here in denominator top, so numerator top, denominator top cancel. Let's see, we have mole up here, and we don't have any other mole, so this one's we're gonna circle that. That's not going anywhere. Okay, now we're ready to come down here. We have liter in denominator top and denominator bottom. We have atmosphere, denominator top, denominator bottom. Again, atmosphere, denominator top, denominator bottom. And Kelvin, we don't have any other, oh, we do. Numerator bottom, denominator bottom, so that cancels with one of those. Okay, and let's see. So we have moles there. Everything is gone there. We have atmosphere there, but we don't have any more atmospheres to cancel with. We have liters and liters, but we don't have any more liters, and we have Kelvin, Kelvin, Kelvin. We don't have any more Kelvin. So these liters, these 3 Kelvins, this gram, and this mole on the very top. So let's write that out. The mole on the top, numerator top. Everything in numerator bottom is gone, so we make that a 1. In denominator top, the only thing we have is the grams. And in denominator bottom, we have liters times liters, so we're going to call that liters squared. We're going to put those back together again. And Kelvin, 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 that's Kelvin squared, or cubed rather. Kelvin cubed, okay? So you're going to flip the bottom up to the top. So all of this comes up to the top. This is already on the top, so it's mole, liter squared, Kelvin to the third, over grams stays on the bottom. It flips over and stays down on the bottom there. And there is your final answer for that. Okay, so we're going to do a Graham's law of effusion here. And with these, by the way, you can round to the nearest whole number for these masses, okay? So the molar mass of He and CO2. Then using Graham's law of effusion, what is the relative speed? Relative speed simply means how much faster one particle is going than the other. It doesn't tell you the exact speed. It just says that this particle is going twice as fast as that particle. That's what relative speed means. Okay, so let's come over here, He. And that is the molar mass is going to be 4 grams per mole. You get that off the periodic table. CO2, let's practice this again. You have 1 carbon times 12.01 from the periodic table. And then you have oxygen, you have 2 of those, times 16. And that gives you 44.01, and we're going to just call that 44. All right, so the heavier particle is CO2, this one. The lighter one is He. So right away, we know that the He is going to go faster. So the rule for Graham's law of diffusion is relative speed. So how much faster the smaller particle will go is the square root of the heavy particle over the lighter particle. So that's going to be and that gives you the square root of 11, and that's approximately equal to 3.3. So for example, if CO2 is moving 10 meters per second, then helium is moving about 33 meters per second, 3.3 times faster. Okay? And that's how you do that. Okay, and number 4 I'm going to leave for you to do on your own. If you don't show the work, you don't get any credit. Okay, and it's a substantial amount of credit because the only problem that I'm not doing for you. The answer to it, though, is 4, but you've got to show the work. You've got to show how you set it up. Okay, that's the answer to this. Okay, that takes care of this answer set for day 48, so let's get those turned in. These are all going to be on the test on Friday, April the 22nd.